Lessons from Lab and Life podcast, brought to you by New England Biolabs. I'm your host, Lydia Morrison, and I hope this episode brings you some new perspective. Today, I'm joined by Sophie Vaud from UK-based Colorifix, a biotechnology company developing innovative new methods for textile dyeing. Sophie Vaud, thank you so much for being with us today. I'm so excited to have you here on the podcast.
Thank you. Pleasure to be here.
So I was hoping that you could share with us the mission of Colorifix.
Yes, so the mission of Colorifix in a nutshell is to replace harsh chemistry with biology in the manufacture and the application of dyes used in the textile industry.
What percentage of dyes used in the textile industry are toxic?
Yeah, that's actually a very good question. So first of all, we might unpack this a little bit. So the textile industry is one of the world's most polluting industries. It accounts for a fourth of the world's chemicals utilized in volume. And depending on the record you actually reference, 4 to 10% of the global carbon emissions. In terms of green gas emissions, that's equivalent to the road and sea transport combined. So it's extremely polluting and it's consuming huge amounts of water. Once again, depending on the reference you're taking, it can account to up to 9 trillion liters of water. Out of these 9 trillions, 5 are used exclusively for the dyeing and the wet processing. So within the textile industry, are particularly interested in this element of the process, dyeing and wet processing, because of the huge amount of water that is consumed and the pollution associated to it, including, as you mentioned, the toxic chemicals. Over 70 toxic chemicals are used daily in the dyeing industry, even today. Out of them, 30 are not retrievable, meaning even after waste management, they are still in the water that is released in water streams, rivers, and so on, damaging considerably the ecosystem and the health of the local population.
Wow, that's really interesting. I actually had no idea that textile manufacturing and dyeing accounted for such a large percentage of greenhouse gases and pollution in our environment. And it sounds like the work that Colorifix is doing is so directly aimed at reducing some of those environmental impacts. Could you tell us more about your role there?
Sure. So I'm head of the microbial engineering division at Colorifix, and my background is in synthetic biology. I have a PhD in synthetic biology from the University of Nottingham, where I developed genetic engineering tools for a bacterium producing bioplastics out of CO2 and other single carbon gas. I have then done a postdoc, again in Nottingham, at the Department of Chemical and Environmental Engineering. And this time I did some fermentation to improve the natural tolerance threshold of microorganisms towards bulk chemicals, with the objective of making them more tolerant towards those chemicals and therefore making them producing more of those chemicals, once again to support the emergence of bioprocesses. And sometimes those tolerances are limitation factors for bioprocesses to be industrializable. So that was great, and that was the first encounter with industry, because this postdoc was in a consortium between industry and academia, and then I joined Colorifix in 2020 as a synthetic biologist, starting to develop colors and pigment pathways to support sustainable dyes. And now here I am.
Well, I'm so glad that you've made it here. Could you explain to our listeners how these microbes, or how you design these microbes to produce this coloring pigment?
Basically, we are looking at how nature produces color, because nature is very creative and has evolved for millennia. So it's actually very good at what it's doing. Nature has a huge diversity of colors but nature is not programmed to scale, at least not at the scale that the textile industry needs it to be. So what we do is that we get inspiration from nature to protect it. Colors in nature are actually often a mix of colorful molecules. So what we do is that we look at the molecules in the first place. We look then at how they are being made in the organism. And this organism can be a plant, an animal, or even a microorganism or a fungus, because there is actually a lot of color in the world of microorganisms, microbes. We look then at the genetic instruction that is responsible to make the color in this microorganism. We copy it, refactor it, and encode it into microorganisms that we can use in industrial processes that are safe, scalable, cost effective, and that we have loads of knowledge and understanding of. So in those industrial workhorses, we encode this DNA and we turn those microorganisms into micro dye factories. We then develop fermentation processes using those dye factories, using beer fermentation processes in order to scale up the production at a scale that is relevant to the textile industry.
Wow, what a beautiful application of science and drawing from nature to identify these colorful molecules. That's really interesting. And I love how you've used the technology from other industries, like the beer manufacturing industry, to be able to grow up large volumes of these microbes carrying this dye. It sounds like it's really the production of the dye process. Like once you get to putting the liquid with the textile, is the process pretty similar?
Yeah, so in short, what is very different is that we don't do any downstream extraction, and so we save a lot of water in the application of the dyes.
Because you've already been using liquids to grow the microbes.
Yes, and there's more to that. We are actually using the microorganisms, or I mean, using is maybe the wrong term, but the microorganisms have two roles. They are those dye factories, okay? And very quickly, actually, the difference between the pigment and the dye is that the pigment is solid version of the color, whilst the dye is in solution, right? So just for the purpose of clarity, I'm going to use colorants as a word to consider the colorful molecule. So the microorganisms has two roles. One is to produce colorants as tiny colorant producing factories. And the second is to help the deposition and fixation of those colorants onto the surface of the fabrics or the textile or even the material we're applying it to.
Oh, interesting. How does the microbe assist in depositing the color?
Microorganisms have evolved for millennia, and they have this particularity that they are very good at adhering onto surfaces. And that might be something you have experienced yourself without realizing. When, for example, tiles of the kitchen or the bathroom don't get cleaned, or then you forget a little corner of the tile when you do your cleaning, then you're going to start to see stains, black, red, or even more greenish stains. And those stains are actually microorganisms, often fungi, that have developed. And they are particularly resistant to cleaning, and you need to scrub actually to apply some mechanical pressure to remove them. So microorganisms are very good at adhering. And therefore, we use this natural ability of theirs to adhere onto the surface and help the deposition and fixation of the dye.
That's really interesting. So the microbes that are adhered to the surface of the textiles, do those get washed away eventually?
Yes. So the dyeing process ends with a short heat inactivating step so that the GM process releases a non-GM product. This is very important. After the dyeing, the fabric is washed and all cell debris and additional or extra dye that hasn't been fixed is removed, leaving then the fabric cell free. And the wash water after 2 washes is actually very clean. So we are saving water in the application, but also in the washing, because on average, a synthetic fabric could be washed up to 7 times, as to remove the excess of dye and chemical auxiliaries, which are those chemicals helping the deposition and fixation of dyes, and that are often used in excess in order to fix the dyes properly. And so that's what we remove from the equation, those harsh chemicals, and also heavy reduction of water consumption in the application and in the washing of the fabric post-dyeing.
Well, that's amazing. I think we've all experienced washing a new garment and having it dye everything else in that load of laundry that you're washing it with. So I'm just now sort of thinking about all the toxic chemicals that released and deposited onto other garments that were in that load of laundry. I love the idea of having a cleaner color depositing system that washes away more quickly and is more sustainable for the environment. I think that's so amazing.
Yeah, just to conclude on that, I mean, to kind of give an idea and give figures, because as a scientist, we always trust data and data driven explanation. And so we have actually run an LCA, or life cycle analysis, to compare a conventional dyeing process to our process. And actually, we compared the application process, conventional application process, to our manufacturing and application process, right? So it was not a fair comparison, but that's all we could do at this time, because it's very difficult to know and to trace the supply chain of dyes in a conventional dyeing process. Once it was actually very easy for us to trace the manufacturing of our dyes, because we know what we use, what we input in our fermenter, our strains, and the media. We trace all ingredients of this media that we blend and sell ourselves to our customers. So we've done this LCA on polycotton, which is one of the most process-intensive fabric that is used in the industry. Polycotton is something you can see actually in bed sheets and other like home furniture. So it's a very conventional fiber, right? And we've observed 53% reduction in the consumption of electricity, but more importantly, 77 to 78% reduction in the water consumption, as well as 31% reduction in the production or emission of CO2. So it's huge. And finally, 80% in the reduction of chemicals. So those figures are real. They are from a scale-up process. And we think it could even be better on different fibers. At least that's what we want to find out.
Yeah, wow. Staggering improvements in water consumption and toxicity and pollution. That's amazing. What kind of materials can be colored with the process that you've developed?
So we've successfully demonstrated that Colorifix technology can work across many, if not all, commercial materials, synthetics and cellulosics alike. And we've tested that in different dyeing processes, yarn dyeing, fabric dyeing, garment and printing alike. And in all cases, for all commercial fibers, we have actually met market standards in terms of textile performance. It's quite unique, actually, if you think about it, because each synthetic dye usually has preferred substrate, so a preferred material it dyes. And this is something that we constantly rethink, and that is not that can't actually apply on sustainable dyes. So it's essentially almost a different category of dyes we are creating here.
Yeah, what an innovative application of microbes. It's pretty astounding. Tell us about the future possibilities for this process. What can we expect to see colored in this way in the next 10 or 20 years?
So we've done a lot of R&D, and when you start dyeing fibers and fabrics, you kind of want to try anything. And we observe a lot of things actually that happen in the lab. So you can think about any surface onto which you conventionally apply dyes, colorants, that could actually be dyed or colored with our colorants, our sustainable biocolorants. So there's a lot of applications that we could open up in the future, think plastics, leather, and so on. But at the minute, we are very focused on the textile industry, which is already a big a big task we have set ourselves to work on. And that's where the industry we want to serve, because that's where I think we're going to see much more impact in terms of water saving and reduction of pollution. So that's our main focus, but there is a lot more we could do, definitely.
Yeah, I'm really excited to see where the future takes Colorifix. And I'm so happy to hear that brilliant scientists like yourself and your colleagues are using their knowledge to engineer biologics to be able to help reduce environmental impact of some of the things that really everybody uses in their daily lives. And the reductions that you're seeing in terms of sustainable use long term and the impact on water pollution, CO2 release, all so important. And I'm just really amazed by this application of microbes. It seems like you've really identified some of the unique individual traits that microbes have and utilize those to really improve a process while at the same time making it more environmentally friendly. So thank you so much for your work, and thank you so much for joining us today to share with our listeners how this technology works.
Yeah, well, thank you so much. I was very happy to be back in a way for half an hour with the NEB team. Actually spent about 8-9 months, now 8 years ago, at the NEB headquarters for a final year internship doing my master studies. I was very lucky to be there. The team was amazing, very welcoming. I've learned so much about science and about a lot of other stuff, art, and in general, a lot of very cool things happening at NEB. Such a nice mindset, innovation, collaboration. I think it helped actually shaping a little bit of the way I see science and how I, I like to drive our projects in-house. So yeah, thank you so much for the invitation. I was very happy to be here, and let's see what the future holds for all of us.
Yeah. Thank you, Sophie. Once a part of the NEB family, always a part of the NEB family, and we're happy to welcome you home today.
Thank you so much. Thank you, Lydia.
Thank you for joining us for this episode of the Lessons from Lab and Life podcast. Please check out our show's transcript for helpful links from today's conversation. And as always, we invite you to join us for our next episode when I'm joined by New England Biolab's own Nathan Tanner. Nathan joins us to discuss NEB's Enzymes for Innovation initiative, and he'll explain how some of these enzymes are being used in new methodologies and applications.